Hi, in this video I'm going to go through a complete set of calculations for labD. However, I'm not going to go step by step as expressed in the lab manual. Rather, I'm going to give it in the context of some cartoons that represent the experimental setup, but ultimately I will show you all the different steps using a set of data so that you can apply it to your own calculations. We'll start on this slide, which shows us the balanced chemical equations for this particular analysis. It also shows us the experimental setup. The potassium iodate, which is our primary standard, is reacted with an excess of potassium iodide and sulfuric acid to produce a defined amount of iodine. And this is titrated with the sodium thiosulfate solution, which is the solution that we're trying to standardize. This solution is found in the burette. So let us start at looking at preparing the primary standard and the calculations that are involved with that. We're told to dissolve around 0.5 grams of potassium iodate in about 50 mils of DI water. So let us assume that we measure 0.5039 grams of the potassium iodate. Now recall that 50 mils of DI water that we dissolve the chemical in, and first of all, that 50 mil volume is not so important. It's just enough DI water to dissolve the chemical. Once the chemical is dissolved, we're then going to quantitatively transfer it to a volumetric flask. We'll be using a 100 mil volumetric flask. So it's that volume, the 100 mils, that will help us determine the concentration of our concentrated potassium iodate. The calculation will look something like this, assuming that we use the 0.5039 grams of the potassium iodate, and then we divide by the molar mass, 214.001 grams, that's the molar mass of the potassium iodate, and then finally divide by the volume of our volumetric flask, the 100 mils, but that's expressed as 0.1000 liters, because of course concentration is in moles per liter. So the concentration of our concentrated potassium iodate will be 0.02355 molar. Of course, to 4 sig figs, given that we're starting with a mass to 4 sig figs, as well as the volume of the volumetric flask allows 4 sig figs. Now this concentration is too concentrated for our particular experiment, and so we do a 10-fold dilution. So we take our concentrated standard, we pipette 10 mils of this into a new 100 mil volumetric flask. So that's a 10-fold dilution. So the concentration of our diluted potassium iodate would be the initial concentration times 10 mils divided by 100 mils. Now note, I expressed the appropriate significant figures here, and also note that I'm using the volume units milliliters. Of course, I could change those to liters, but the units cancel anyways. So the new concentration, the diluted concentration, would be 0.002355 molar. If you compare those two numbers, you see that they differ by a factor of 10. So hopefully that makes sense to you. You could also arrive at doing this calculation if you use the C1V1 is equal to C2V2 formula. So that formula or equation can be used for doing dilutions. So now that I know the concentration of my dilute potassium iodate, I can calculate the moles of potassium iodate that will be delivered to the Erlenmeyer. So note, we're told that we're going to pipette 10 mils of that dilute potassium iodate solution. So I know a volume, I know a concentration, I can calculate the moles of potassium iodate in the Erlenmeyer. 0.002355 molar times 0.01000 liters. Now note, in this case, it was important that I use the units of liters because, of course, the units for concentration are moles per liter. So the units, of course, have to match. Therefore, the moles of potassium iodate that are delivered into the Erlenmeyer would be 0.00002355 moles. Now, of course, this is probably better expressed as scientific notation, but either way, as long as you know that that's the moles that have been delivered. Now that I know the moles of potassium iodate, I can use my balanced equation, shown there, number 1, to determine the moles or the amount of iodine that would be produced. And it's based on the fact that it's 3 moles of iodine for every 1 mole of potassium iodate. So I take those moles of potassium iodate times 3 moles of iodine per 1 mole of potassium iodate. Therefore, the moles of iodine that would have been in that Erlenmeyer 0.0007064 moles of iodine. It's this iodine that reacts with my thiosulfate standard solution. So the next step is to determine, well, how much sodium thiosulfate reacted. Note that these need to react to the stoichiometric point. So the moles of iodine will define the moles of the thiosulfate that are required. So the moles of the sodium thiosulfate that reacted, based on this balanced equation number 2, will be the 0.0007064 moles of iodine times 2 moles of the sodium thiosulfate per 1 mole of the iodine. So therefore, this number here, 0.0001413 moles of the sodium thiosulfate, that's the moles of sodium thiosulfate that reacted. That's the amount of sodium thiosulfate that was required in the titration. We're getting closer, therefore, to determining the concentration of this standard. What we need now is what volume was used in the titration. So we want to determine the volume of the titrant. Now we'll assume that we did this titration 3 times. So here are some numbers. We're going to take the mean of those numbers, and we're also going to calculate the standard deviation. We'll calculate that standard deviation either using a calculator or using an Excel spreadsheet. The standard deviation in this case comes to 0.08. Note, standard deviation is always expressed to only one significant figure, and its decimal place will dictate the decimal place that we're allowed to express our mean value. So note, it's to the hundredths position in the standard deviation. We're allowed, therefore, to express the mean to the hundredths position. If that standard deviation had been 0.1, we would have had to have rounded off the average volume to 13.2. So do recall, or do keep this in mind when you're doing your calculations. Now, because I'm going to use this mean in a further calculation, I need to know what the relative error is. So the standard deviation is an absolute error. I need to change this absolute error into a relative error. Therefore, I'm going to take that standard deviation and divide by the mean times 100%, which gives me 0.6. That's 0.6%. I will use that in subsequent calculations. Note, the relative error is also expressed only to one significant figure, but its decimal place does not dictate the decimal place for the mean. All right, so do keep that in mind. It's only the absolute error that dictates the decimal place. Note, the absolute error and the mean have the same units, so keep that in mind. Next, finally, the concentration of the sodium thiosulfate. So I have the moles of the sodium thiosulfate. I will now divide those moles of the sodium thiosulfate by the volume. I end up with this number. It is this number, 0.01068 molar, to this particular relative error. As a side note, when you actually do your own calculations, you should end up with a concentration that's quite similar to this, because the data that I'm using for these calculations will be similar to the data that you will be using. I can't leave the number like this. I want to know what is the absolute error. So I'm going to convert the relative error to the absolute error. So I take this concentration and I'm going to multiply it by 0.6 divided by 100. Of course, 0.6 divided by 100 is the same thing as percentage. So in other words, I'm trying to find out what is 0.6% of the 0.01068 molar. When I do this calculation, I find out that the absolute error, that is 0.6% of 0.01068 molar, is 0.00006. Again, we only express the absolute error to one significant figure, and The decimal place of the absolute air dictates the decimal place of my concentration here. You can see, however, that they all line up to that 5th decimal place. This is the final result. This is where you're trying to get to when you do your calculations. I hope that you have found this video helpful in setting up your calculations.